Okay, here we are in the lab again, and this is episode number 8 of Build Your Own Main Brain Microcontroller project. So the last video we finished up the configuration registers uh, for the oscillator. So then now this episode is about the core. So a PIC microcontroller, regardless of what model and family you have, it's a system on a chip. So that means it has a microprocessor inside, as well as RAM memory and ROM memory. And in most cases, it's flash. So you can reprogram it, and you can even update it in runtime with like a bootloader, so you can update your firmware. So, and then it has various peripheral devices like a USB or Ethernet, SPI, I2C. Then it has some interfaces like the PMP, peripheral main interface, and it also can, some of them have specific graphics modules to interface with LCD modules. And there's a wide array of peripherals that are available for different families and part numbers of the PIC. So in this video is what we're going to focus on is the core. So inside the PIC32MZ family is a MIPS 32-bit core. And MIPS is just, it goes back to the 90s. MIPS is, I guess, is the company that originally made it. So that's where the MIPS comes from. It's a reduced instruction set microprocessor, and the core runs at between 200 and 250 megahertz maximum. It has a 5-stage pipeline, 32 bits internal with a DSP and an FPU. We won't go over the trace and the enhanced JTAG. That's for later debugging stuff. It has an instruction cache and a data cache. That's the level 1 cache. We'll cover all this. Okay, taking a deeper dive into the core. Starting from the right, there you have the system bus, and then that interfaces with the bus interface unit, kind of like an arbitration thing. And then you have the instruction cache and the data cache, some power management there on the bottom. Then each cache has their own controller. The MMU is the memory management unit. Then you have the MIPS decoder for the MIPS assembly instructions. And then the execution unit, which is like the arithmetic logic unit, does like atomic bit manipulation, has some DSP application specific extensions. So it has some DSP assembly instructions. Then you have the system control coprocessor. So that is an important thing we're going to look at in the code. It has to be configured somewhat. And then there, up at the top, we have the extended JTAG interface. And then that's part of the debugging and profiling, breakpoints, trace, all that stuff for debugging. And then we have the GPR, which is the general purpose register set. There's 8 sets. Then the floating point unit, we'll configure that in code as well. And then some specific application-specific extensions for the MIPS, and then an enhanced multiply divide unit. So that's for the math, and they have some DSP extensions as well. So with the 5-stage pipeline, the idea is to overlap the instructions so that when a normal instruction would take multiple instruction cycles, if you overlap the instructions, you can get 5 instructions in like 9 clock cycles. So you can see how much more efficient it is to do a pipeline. So we won't dig down into it real deep, but just a pipeline, the 5-stage pipeline just means that 5 instructions are overlapped to fit in like 9 instruction cycles. And that can be hampered by branches and stuff like that affect the program counter. But because it's predicting what the next instruction is, so anytime you predict the future, it's not exactly 100%, but you do increase a lot of performance by using this pipeline. So that's why they have it in there. It really increases your performance. Now, as far as the DSP, it's an extended set of assembly instructions to do digital signal processing, specialized arithmetic instructions, to do saturation and fractional math. It's for like if you work with audio and stuff like that, you're going to probably want to use that. We're not going to get into it in heavy detail. We'll move that to a later date when we have to actually use it, and then we'll cover it. We'll just move on to the next subject for right now. Okay, so the floating point unit. So in the MIPS core, the floating point unit is implemented as coprocessor 1. It handles floating point arithmetic, and it's optional in many designs. It's a separate execution unit for floating point math. It uses its own floating point register file. It operates in parallel with the integer pipeline, but it is tightly coupled to it. It has 32 floating point registers, FO to F31, and each register can hold 32-bit precision, or you can pair them for 64-bit double precision, and it's controlled by the floating point control and status register. So the floating point unit has to be enabled in code, and you have to set your compiler up to compile for the FPU. Otherwise, it will use software processing, which is much slower than the hardware FPU processing. Okay, so as I said before, the cache is a level 1, L1, which means that it operates at the same speed as the microprocessor. So the I cache is the instruction cache, where instructions are read from program memory, from the flash, into the cache. And D cache is the data cache, which is a write back cache, or uses write back. And so write back is when, different than write through. Write through, the CPU writes to the cache and the memory immediately. The write back, the cache, CPU writes to the cache only, and it's deferred for a while. And so the way it works is the CPU finds the cache line containing some data, and then the cache line is updated from a data buffer. All right, and then once it's written into the cache, then it's marked dirty, but no memory has changed yet. So then another cache line needs the space eventually. So the line that's marked dirty is written back to the RAM, and then the cache line is replaced. So why do this? Well, it takes fewer bus writes, and multiple CPU writes collapse into one memory write. So that's saving time. And that makes for much faster loops and structures. All right. But there's always a drawback. So the memory can become stale, and the DMA peripherals may see old data. So the software must manage it by what they call coherency. So we'll get into that a little bit later when we're writing the actual code, because there is a coherency thing in the code that we have to deal with. Okay, the shadow register set is a hardware feature to make interrupt handling very fast. And they do this by avoiding most of the register save and restore overhead. So normally when an interrupt occurs, before you can service that interrupt, you have to save certain information like the program counter and different registers that are going to get, any register that's going to get changed from that interrupt service has to get pushed onto the stack and saved. And then once the interrupt routine is serviced and returns, before anything can happen, all those registers that you pushed onto the stack have to get popped off of the stack, and then the program execution can continue from where it left off when the interrupt occurred. All right, so that takes dozens of cycles and eats up time, CPU time. So in order to eliminate that problem as much as possible, they create shadow registers that shadow everything that's going on in the registers. Normally is shadowed in another set register bank, another set of registers. So it's like a mirror or an exact copy. And so when the interrupt occurs, then it switches to that register bank and starts executing the interrupt service routine. And those registers can change because the main registers, the original registers, are unchanged since we switched register banks. Okay, so then once the interrupt is serviced and it returns, it doesn't have to pop all those registers off the stack because they're already in the original register bank. So even though the registers changed in the current register bank from the interrupt service routine, the CPU switches to that original register bank, and you can just start executing like nothing happened. And that saves those dozens of cycles of CPU time. So in our context, our CPU, the PIC32MZ, has up to 7 shadow register sets. So you can pop through each of those shadow registers instantly, depending on, and you can set it up to what interrupt priority is used for which shadow register set. All right, and you specify that in the PRIS register, PRISS, that you probably noticed in the code from before. That register maps which shadow register set goes to which interrupt priority. So normally you just set it to where interrupt priority 7 goes to shadow register set 7 and on down the line. That's usually the way you do it, but you can do it however you want in whatever order and mix and match whatever you want. Okay, so that is the basics of the core. So let's jump over to our code or my code and check out, and I'll show you how I implement it, and that'll give you guys some examples of how the actual code is used in the real world. Here we are in our code. So the first thing, we have a couple new pragmas here that we have to add. So this is for to enable the floating point unit. So, well, enable the code context for the floating point unit. And so you have to put in the specific part number that you're using, all right, as defined by a microprocessor. And then this is the hardware. This tells that you're going to use the hardware for floating point math. Okay, so if you without that, it does it in software. So it takes a lot of software stuff to do that, a lot of power. So this will take the load off of the software whenever you use floating point calculations. If you don't use any floating point, you won't probably notice anything. But this is we got to put these in up here at the top, and then we come down here, and in our system setup, then the first thing we must do, or one of the first things, is this is your PRIS right here. You got to define your shadow set and map it to the interrupt priority. All right. Then we did the clocks last time. So this is turning on the floating point. Even though floating point is CP1, coprocessor 1, you turn it on in the status register of the CP0, the coprocessor 0, which is the system coprocessor. Okay. And so that's pretty much what you're doing right here. All right. So you want to right click on your project, select properties, and then you want to select your compiler. And then under here, under additional options, you just want to type in this. Tells it the hardware, the floating point compiling must go with the hardware. All right. The floating point unit. All right. And that's all there is to that. Okay, so now that you have the floating point turned on, let's go and look at the PRIS register. So this is how the PRIS register is implemented. And you can see that it's just 7654321 So that just maps all the registers. Like 0, you can't really change that. You can't like make it a 1 or a different priority. But all the other ones you can, but 0 you cannot. It's always 0. And so this means that shadow register set 7 goes with interrupt priority 7, and shadow register set 6 goes with interrupt priority 6, and so on down to 1. And that's all you have to do for the shadow registers there. However, you have to implement that in your interrupt handler. So we will come down here, and here is an example. This is the change notice interrupt handler. So that's IPL for interrupt priority 7, and you have to tell it to use the SRS. So that's the shadow register set.
All right. And you got to tell it no MIPS 16. I don't think you can, I don't know how, if you use MIPS 16, how it would affect that yet. I haven't got that far because I don't use MIPS 16, but you should tell it no MIPS 16 and use the SRS style of interrupt. So this is the way you structure your interrupt handler. All right. So you put the vector in here, the name of it, that is in your data sheet. That has to be specific to whatever vector you're coding. And then, like I said, the SRS for the interrupt priority, no MIPS, and then you can call it whatever you want right here. All right. And then you put your code in here. You always got to remember to put your flags back, reset your flags so that another interrupt can occur. And then whatever you do in here is up to you. All right, so that's how you do the shadow register set, which greatly speeds up your interrupt service routines.
So one thing we have to touch on is the memory segments. So in the MIPS 32, we have two views of the same physical memory. We have KSEG 0 and KSEG 1, all right? And both of them are virtual views of the same physical memory. The only difference is KSEG 0 is cached and KSEG 1 is uncached, because there are times when if you use cached memory for some variables, they're not going to get changed and your program's not going to work right. So for those kind of variables where you need them to be volatile and change right away when they're supposed to in real time, then you have to organize them into the KSEG 1, all right, which stands for kernel segment, all right. And so some things can be cached, and that's what you assign to KSEG 0, all right. And these are kernel segments. They also have user segment, and we'll get into that later because your firmware basically runs in kernel mode, in the kernel memory. One thing I should mention before we move off of here is that when we turn on the floating point unit, we are making bit 29 of the CPU or the coprocessor 0 status register a 1. So coprocessor 0 status register bit 29 turns on or off the FPU. Okay, so then we want to go up here a little bit and then we'll do our cache. So you have to turn the caching on for KSEG 0, and so we do that right here. Okay, and we enable the cache basically almost the same way we did the FPU. The only difference is the FPU we write to the coprocessor 0 status register, but for the caching, we write to coprocessor 0 config register. Okay, so that's what the 16 is the config register. And as what we're doing is we're setting the first thing we're doing is we clear the lower 3 bits. So we clear them to 0, and then we write 011 in there, which is 3. And so this is the recommended setting. So it's what it does. It enables write back and write allocate caching for KSEG 0. All right. So it enables instruction cache enable
data cache enable, and write back policy, and write allocate on store miss. So I'm not going to get deep into that. That's the recommended setting. And if you want to explore deeper, that's great. And maybe we'll explore a little bit deeper into it later. But for right now, that's pretty much all you need to know. All right. And then one other thing, right after you write to the config register, you must insert this barrier here. And so this is a barrier so that subsequent instructions don't execute with a stale configuration bits. So you want it to force that to be changed before you execute more code, so that it's not a stale or invalid data. So there's one last thing I want to show you, and it's in the system setup as well. So if we come down here, and if you remember from before, once I configure stuff, the clocks and stuff, then I speed the clock up. And before, 56 was the highest I could go without being unstable. And so I did a little bit of studying, and now I have it running solid at 60. So that should be our maximum 252 megahertz, or real close, maybe even a little over. I'll have to check. We'll check on that on maybe the next video or so. But the way you do that, the problem was the wait states for the flash. I had to raise the wait state right here for the flash. All right. The prefetch access time, which is defined as system clock wait state. So before it was at 2, and when I set the system clock at the 56 setting, that was cutting right on the edge. So if I had to increase one more, I had to add one more wait state for the flash. And now this is the internal flash of the microcontroller. All right, so I had to increase the wait state to 3, and then that gave it enough time that it can write to the flash reliably. So that was the problem. So now I'm up here, I'm running at full speed right now. All right, so the core is running at like 460 megahertz or something like that. It's just humming right along. So, and it runs good. I haven't had any problems yet. So I just wanted to mention that, because that is a pretty important thing. Okay, so there's the core, the basics of the core. That's what we need, the minimum level of knowledge about the core to get some firmware up and running, and get it running fast and smoothly. Because if you just run, like, that's how I started the first time. I just started writing my code, and I'm like, this thing is running too slow. And so I got on the forum, Microchip forum, and they told me, you got to get caching and stuff like that enabled. So once I did that, it moves along pretty good. I have some pretty good graphics that I work with on MainBrain for the menus and stuff, and it pumps that screen along pretty good. It can actually outpace the screen if you're not careful. I think the PMP, the peripheral main port, I have some pretty good wait states in there for, like, the external flash. Even though it's 70 nanoseconds, I have to have quite a few wait states, and a few wait states just to make the write, or the write pulse and the read pulse is wide enough for it to detect. Because at full speed, those pulses are really tiny. I'll have to show it to you sometime on the scope. I mean, they're really thin. And so some hardware can't detect that fast of a pulse. So you have to stretch it out with some wait states. And it's not my favorite thing to do, but you just have to do it and you have to live with it. But it's still, this processor runs really good for it's a pretty good microcontroller. I really like it. So yeah, that's the core in a nutshell. So that'll wrap up this video, and then I don't even know what we're going to do on the next video. I'll have to think about that. Uh, yeah, I'll have to think about that. So I will see you in the next video.